Okay, our next talk is going to be Ingrid, who's going to tell us all about silicon detectors and the R&D towards our next greatest silicon detector, I suppose.
Let's see, next or next to next
Yeah.
or next to next to next.
Perfect.
Okay, can you hear me? Yes. So first of all, thank you very much, Lawrence, for this very nice presentation. It already covered a little bit of what I don't have to introduce anymore, which helps a little bit now. So I was asked by Federico, who helped organizing, to give a rather basic talk, what you always wanted to know about silicon detectors, and that I added a little bit on stuff which go a little bit beyond the very basics. And so, does it work? Yes, it does work. I mean, just going back, there are silicon detectors almost as long as people know how to build a PN junction. I will explain what a PN junction is in a few minutes, but nevertheless, I was always amazed, like they put together two types of silicon, realized that they can do things with it, and shortly after they started to use it as detectors. So that's actually quite amazing. And I think by now it's also something like 65 years that semiconductor detectors are used for measurements, and here are some really nice ones, and I kind of used them because I was at some point involved with one or the other in my early career. So we'll talk about silicon as a detector, then I will introduce a little bit on strip detectors and pixel detectors and what's up for the next generation. So first of all, tracking detectors, we already heard about them. Tracking detectors are used to measure the precise momentum and the track itself of charged particles. So this is always important to keep into mind. Non-charged particles we just don't see. We have to then add other information from other detectors, or maybe a little bit of conversion of photons nevertheless, but what I'm talking about is for charged particles. And then the momentum resolution, which is done depending on the position resolution, the momentum, the magnetic field, and the level arm. So how big is the length between the interaction point and the outer, so the radius, so where is the last measurement within our tracker. And so there are already quite a few things which we can use in order to optimize the detector, especially the position resolution we want, but also the level arm. The larger the better, the stronger the stronger the magnetic field, the better. But also the position resolution is then something which I get from my actual strip detector, and not shown here. Material is in there. The more material, the worse. So we have to reduce material in our detectors. So we have tracking detectors in quite a few of the HAP detectors. So here's an example of CMS. So this is something like 15 meters. And in the first, let's say 1 to 2 meters, we have then tracking detectors. In CMS, there is currently a full silicon detector, and will stay like that also for the future. And what is also to keep in mind, but I'm not going to cover it today, next generation calorimeters are also using a lot of silicon in the future. And we are actually moving towards tracking calorimeters, which is for the muon collider probably very, very interesting, so away from what we have now. But I will focus this talk on classic silicon tracking detectors for the innermost region. So also to look at the vertex detectors a little bit, because they are very important for any high energy physics experiment. So I actually also have one slide on the Meyer concept, as already introduced by Lawrence. So this is this new detector concept, and I didn't have such a fancy picture as Lawrence, but nevertheless, it is also important because this is a way detector people very, very often show a tracking detector. And the person who hasn't worked with that has no clue what we are talking about, because this is a bit hard to know. This is actually a quarter segment of the detector. So here is the interaction point, and this is then the Z direction along the beam pipe. So in millimeters, typically given. So this is something you see above 2.5 meters long. That means the detector is 5 meter long. And then the radius in millimeters going up here. So that is going then to 1.6 meters. So that's quite then the radius of the overall tracking detector will be 3.5 meters. This is the focus on the tracking detector. And this is what one has to keep into account. And then very often you hear about people talking about ether. Ether is the pseudo rapidity, and then ether here going straight and with 90 degrees from the interaction point, that's ether 0. While going towards the beam point, we are going to infinity. And then, for example, here we have something which is 2.5. And then this is a very interesting region. So this is very often where we are struggling to put detectors, because you can imagine this close to the beam pipe, it's very hard. But theoreticians, of course, want us to measure down to ether infinity. And this is, of course, not easy to cover. So the key challenges here in the muon collider are the beam-induced backgrounds, because if you have a single event, you will get in the order of 100,000 induced background hits versus actually just something like 10 to 100 signal hits. So that gives you already an idea of how difficult it will be to disentangle whatever is in the tracking detector from beam-induced background to real events. And this was also shown before. So this is how the detector is set up. There is a pixel detector inside here. There is another inner tracker here and an outer tracker here, there. And this is very often how people, how in particle physics detectors are shown. There is a vertex detector, inner tracker, outer tracker. But sometimes the outer tracker can also be the muon detector way outside of the silicon tracker. But before going to that, I'm going a big step back, and I will explain what is a semiconductor and how does it work as a detector. So here, just very basics. You remember probably from a long time ago at university that you have various possibilities of material, that you have a metal where actually the valence band within the atom and the conduction band are overlaying, or they are rather apart, so that we have a huge forbidden band so that the electrons from the insulator can't get into the conduction band. And with that, we're insulating. As the name already says, semiconductor is something in between. So we do have actually here a forbidden band, but it's not that much so that actually electrons can get from the conduction band into the valence band, for example, with temperature. So that there are sometimes electrons in the conduction band, so there can be some conduction, but not that much. And this is actually something we can use in semiconductors. So, and just because silicon is something we use a lot, this band gap is only 1.1 electron volt wide, so the difference, but actually it takes 3.6 electrons get an electron here from here to there. For example, with thermal energy, and the rest is actually going into the phonon excitation, so into the heat. So there is already a loss there. So remember, 3.6 electron volts will put an electron from the valence band into the conduction band. And now a little bit more on the band model. So you can imagine here the crystal structure of a silicon here. And if you press it completely flat, you can imagine to be like that. So for every silicon, we have 4 neighbors. So every silicon atom has 4 neighbors, and they do then this beautiful covalent bonds so that they share always electrons here together. This is at 0 Kelvin. But as soon there is already a little bit of temperature, they are actually going into the conduction band and travel around. And very, very important about semiconductors is then that you not only have here the electron, which is a negative charge, but in semiconductors, we also look then at the hole. The hole is here, and the hole is then considered as a positive charge. And that makes it so interesting, and that one has to really understand that you have in silicon detectors negative and positive charges. And I will use that in a moment. But here you see already just a little bit above the 0 temperature, you already get the first electrons in there. So if you look, for example, in the ultra pure silicon, meaning that there is nothing else in this crystal than silicon, you get already 1.4 10 to the 10 intrinsic carrier, so electrons at room temperature. So there is already quite a lot of electrons traveling around in the silicon already at room temperature. That's also something to take into account. So here, you know this Bethe Bloch from the particle data book, where we can see how the ionization is behaving along the momentum. And if you focus, for example, to the DEDX for a proton in silicon, look here at the MIP, we actually see that we have a DEDX we get of 3.87 MeV per square centimeter. So this is the mean energy loss per flight path for a MIP through silicon. While for the mean energy loss I just already mentioned. So if we take now a piece of silicon, be it 300 micrometers thick, so just like that, and send a MIP going through it, like here, then we can calculate now the signal for the MIP in this detector based on the information we have, the DEDX. Only EV. Sorry, I will fix that typo. Anyway, that we, no, it's 10 to the 6. No, stupid. It was 10 to the 6. Yes, of course, this is MeV. And then if we calculate this DEDX over the distance here with this mean ionization in mind, we actually see that when a MIP goes through silicon like that, we get 10 to the 4, 30,000 electron hole pairs. Nice signal, that's good. We can do something with that. The problem then is what I was saying before, this intrinsic charge carriers, which we already have, that is in the order of 1.4 10 to the 10. If we take that then for this volume, we get actually 4 10 to the 8 electron hole pairs in that at the same time. So we will never ever see a MIP in this because it would swamped with this electrons we have at the temperature. So smart people came then up with doping of silicon, not only at the Tour de France, but here now we have the possibility to do something about the silicon. So the smart people, they came up that they actually add here additional borons, which have 5 electrons in the conduction band, valence band, I'm sorry. So with that, there is an additional electron which they add in the crystal. And that's done here, adding additional energy levels in the forbidden band. And with that, we get more electrons. We call them sometimes donators, but that doesn't make a difference here. Or at the same time, sorry, phosphor was that, with the additional electrons, and borons have only 3 electrons in the outer layer, and therefore we introduce holes. And this is what we do then. We call this N silicon, and we call this P, because here we have more holes than a normal silicon. And in the other one, we have more electrons than the normal silicon. And this is how we distinguish them. N-type, more electrons, P-type, more holes. And what then smart people came up with is to put them together. So if you add a P and an N-type material close together or add them together, we deposit them on each other, then something interesting happens, that then actually the electrons from the N-type material diffuse into the P-type material and sit there and then in the holes, and then the holes are gone. And on the other side, from the P-type, the holes are moving over to the N-type and then close here, capture here the electrons. And with that, we actually get then an area which is free of charges, so that all the electrons are gone here and replaced by holes, and all the holes are gone here and are replaced by electrons. So in that area, we don't have any charge carriers anymore, but because it was neutral before, we actually introduce an electric field at the same time, because we have actually more electrons than original on this side and more holes on this side. So with that, we increase an electric field. And then we have a detector. If a particle goes through, we have here no other charges anymore, so we can actually already measure our MIPS, for example. Easily done. So at this boundary, here that you heard this word, a depletion region is formed. So that's what we are interested in, to get this depletion region. And this has an electric field and no mobile charge carriers. And when we apply even a voltage from outside, which we call bias voltage, we can increase this depletion region from one side to the other. And really, the more we have, the larger we have, the more signals we get when a particle goes through. And this is how a silicon detector works. I have here a small animation. So we have, for example, 300 micrometer thick. This is, for example, an N-type silicon, and we introduce here with the surface implants these PN junctions. When we apply a big voltage to it, we can actually deplete the full area. Then we have a depleted area, a charged particle goes through. Then we get our electron-hole pairs because of the ionization. So particles go through, ionization, and then I can collect the signals here, and I have them here wandered to the nodes here, and then I get actually a signal here depending on how close the particle was going through the channel. You have a question? I'm sorry, I acoustically had problems to understand the question. I heard you speaking, but somehow the words were not very understandable. No, yeah, kind of. Yes, it's a PN junction, which is a diode, yes, and it's in reverse bias so that we get the region third. But it's not that I mean, if we open up the diode, we break the detector. So we don't want that. So we really want to have very small signals going through, which we then measure. Yes. Okay, now I understand your question. Yeah, so and then in the readout electronics, we can then apply, if we want to, depending on what kind of detector we have, we can do an analog readout, read the height of the signal, but that's very tedious. Nowadays, we go to the so-called digital detectors where we say there is a threshold. If the particle was above the signal was above the threshold, we know there was a hit. And this is very basic how a silicon detector can work. There are multiple ways of how to do it, but I will not go into this today. Okay, so with that, I introduced how a silicon detector works. And then there are multiple detectors around how to do them, and currently also running. So a classic silicon strip detector is indicated here, so that we now make channels inside our silicon, for example, along the silicon, which we call strips. They can be shorter or longer. And then when we have a particle going through one of the strips, we know the hit was in that strip. And by, for example, adding another layer underneath with a slight angle, we can even then find a bit more information where along the strip the particle was going through. This is a very established technology. We use it in most of the silicon detectors, most of the high energy physics experiments. For example, currently we are building huge ones for the high Lumi LHC. And then, so that's a very basic concept, that we have the silicon detector, which is then divided into strips connected to some front-end chip. And this is typically done with wire bonding. This is a technology that you put 15 micron thin wires directly to it with the ultrasound glued, not glued, melted to it. Here, detector, which is already around since quite some time. So here you have the silicon detectors. They are just here the strips in this direction. Here you have all your information that picks up the signal, digitizes it, and brings it to the outside world. And if you look very careful, I should go here, I'm sorry. If you look very careful, there is actually hinted that there is a second layer behind it, which is rotated by a few degrees so that we have this stereo angle so that we get more information where the particle was going through along the strip. And the challenge is that if you have many particles at some time you can't distinguish where which hit was from which track. And also, believe me, this is not easy that you connect all your strips to a readout electronics single by one. It's a lot of work. And there are system aspects I will get in a few minutes too, which might make life very hard. Nevertheless, these beautiful detectors were built. Here is an example of the silicon barrel section. So when you look here, the particles hit here in the middle of the screen, in this here. And then we have barrels, we call them like the barrels for beer or whiskey. We put around the beam pipe, that's the barrel section. We also have then discs for the forward region. And this is one of these barrel layers. And one of these is each time a large piece of silicon made to a module which is reading out that. And then if we have particles going through the various layers, we can actually measure that. And then this is just how beautiful work is being done by all these technicians doing this handiwork, attaching the modules here on, for example, the Atlas of SCT and CUP. Also another, I will not go into the details here, but it's a beautiful shot. This is the same detector, not the same detector, a similar detector, also a strip detector. So these orange things, where they are not orange, they are just orange because of the light the photographer wanted to have. These items are the silicon, and then here is the electronics which picks up the signals from the wafers, from the silicon piece. Okay. These are now running since more than 15 years. This is amazing, actually. Here is a picture, an event display. So that was a real event on the trigger. Recently, I think this one was from March this year. There's the pixel detector and there's the strip detector, and you can see how many tracks at the LHC have to be measured in one collision. And here is a somewhat complicated plot. I will not go through all the details, but there is something which I don't have time today, which is actually the radiation damage, but it will be a problem also at the muon detector. So the more radiation you have, the more current you get, for example, in the detector, and you have to make sure that you still can distinguish the detector, the sensor current from the signals. And therefore you have to, when you design the detector, keep that into mind in your electronics and so on, that you actually have the current somehow under control. And what is nice about this plot is there is this, for example, it's called Hamburg model, because that people introducing a model to describe how this current will go up with the luminosity. And this shows nicely that this actually worked quite well, that the Hamburg model fit with what the luminosity was measured. And that was actually extremely exciting for a silicon detector person to see at the very beginning of the LHC that these models really work, because we were very worried about if these are really working. And the take-home message from this plot is even under more severe conditions, because it was already mentioned by Beniamino yesterday that the conditions were actually more severe at the LHC than expected. Excuse me, the detectors work reasonably well, and we are actually quite happy, and they have to run another year, and then we have to take them out. So so there are a lot of strip detectors around here, just a few examples from the STAR experiment in the United States, a strip tracker. There is a satellite experiment. This actually sits on the ISS, so this is the AMS silicon strip tracker, so this is about 3 meters in this direction. An old strip detector from the Zeus MVD, which was taken out in 2007. And there is also from CDF, the strip tracker. So various detectors, and then we are also building some right now. So we go for the high Lumi LHC, as you've seen yesterday, and where we have the original detector we have designed for something like 20 to 55 pileup events. Pileup events are the ones which we get at the same time for one collision, because there is not only one collision, the one we are looking for, but because of the bunches, we actually get up to 55 pileup conditions, and we even saw now like more than 70 or something like that. So this is already rather crowded in the detector, and the detector has to be built to actually distinguish these tracks. And then in the future, for the high Lumi LHC, we are looking at up to 200 pileup events and maybe even more. So for that, we had to rebuild the detectors. First of all, the current ones are going to die anyway, but the second of all, the next one has to be more with smaller strips, smaller pixels, more robust, and therefore we had to build new sensors and that. So because of that, for example, Atlas and CMS, I'm kind of focused a bit more on Atlas. I don't know why, but I try to have CMS here and there once in a while. So here is the picture is actually from Atlas. I've tried to find nice pictures from CMS, but it seems that my computer just doesn't want to show CMS stuff, because I really tried, but I only found Atlas, Atlas, Atlas. So I had to go for an Atlas plot. I think, we have to bribe my computer or something like that. So this is what we are going to build. We are going to replace the current strip, including the gas detector we have in Atlas, by a full silicon detector. And then we have in the innermost area a pixel detector. We'll talk about that in a moment. And then we have a strip detector. Again, this we call the barrel section. And then we have here the end cap sections. And out of funny reasons, I have end cap pictures, because at DAISY we are going to build 2 end caps. So one for CMS and one for Atlas. So I have here the CMS end cap, and then here the Atlas end cap, just as an example. There will of course also be a barrel section, but all together, each of the experiments have to build 20,000 modules, and each have to build 150 square meter. I guess this room is 100 square meter of silicon. So that's really a lot of work. And therefore, currently the community is gearing up, or not only gearing up, they are starting to produce right now. So how to produce a detector? You do the module production. Modules are pieces of silicon with electronics. So you have to attach it somewhere. You do a module production, and you also need some support structure, some mechanics, maybe some cables, some cooling, and so on. That here. Then you put that together. You make parts, you make lots of parts, and then you put that together. We call that integration. Sometimes we call the integration just putting together, but then there is another integration that we take the thing and put it into the big experiment, and then we want to commission it, meaning that we want to run it. Done. Very easy, very, very easy. The problem is now the details. First of all, we have lots of parts. We have already, be it the capacitances which sit on the electronics. They have to be radiation hard. Every single glue has to be radiation hard, and so on. So we have parts for the support structure. Every single screw we have to understand. Then also when we put things together, we add more things to the detector. These are parts. And also there, in order to bring it together, there are parts coming from a lot of places. And then we have to do the testing. Every single item has to be tested single, then when put together with one thing, then when we have a module together, when the module is on the first stave, and so on. So we are working on that. And unfortunately, also while we are doing that, we find problems. And then we go a step back for back, forth. And so we are trying to build these detectors, but it's super difficult. And so that makes it really the complication. And hundreds of people are working on this, and everybody is working really hard. And still we are stumbling quite a bit. Just as an example, this is the workflow for one end cup at Daisy. Not both of them, just one of them. So it will not drag you through this plot, but just to let you know, we have various labs involved in order to build this detector. We have companies who send us stuff. So that we have to order the stuff either through CERN or ourselves. It has to arrive. We have to test it. We have to have a person who allows that we spend this money and then we have other institutes to deliver us things, either modules to put them also on our structures, or they bring us bigger structures, or from NICEF comes the mechanics and so on. So all this we have to keep under control. And that is nice with Beniamino's talk yesterday. Everything has also its problems and contracts and management and then just one example of what can go wrong in building such a huge thing is the module crash. We lost 1.5 years because of that. When I see, for example, the CERN research director, I jump somewhere behind the bushes so that he doesn't approach me on that, because they are pushing that we are done. Find this problem here. So there is a crack in the silicon. And it's not in an obvious place, but they were hiding under the electronics or somewhere. So suddenly our modules were breaking. Of course, you say to the first institute, who has the problem, you did something wrong. Do it again. Oh, broken again. Oh, also broke at a different institute. Oh, this is really getting, and then in the end, it was a problem that we had so-called CTE mismatch, meaning that the coefficient of thermal expanse, which we call CTE, was too different. And that makes thermal stress. And then the weakest part was the silicon, it broke. You might say, yeah, but that's something known. Physicists know. Why didn't you see that? Yes, we knew about it. We knew, and therefore we designed the detector to be fine up to minus 35 degrees Celsius. Only recently it became clear that there is a unlikely but still possible scenario when the cooling has a certain problem, then that the detector can go to minus 55. So we had to test to minus 55, and boom, we had these cracks. We solved the problem. We put some more, a little bit of material into it. We had to redo our module construction, how to do it. It's a lot of work. Hope it works. But just to give you a glimpse at how things can badly work. Okay. Going to the innermost part of the detector. I still have 20 minutes. Okay, that will. Okay. So I was talking now for the bit more the outer part, that we have the strips, but nevertheless, if you have too many tracks, at some point you might not get the right information before strip distinguish anymore if the hit was belonging to the track or not. And therefore, already very early on in the 80s, they came to the solution that one doesn't segment only the silicon, but actually into small squares, which we call pixels. But then you have to see how to read this little square out. And this is how pixel detectors were invented. First, there were, for example, CCDs, which were also used for cameras. But then later on, hybrid pixels were developed, which I will introduce. But the first pixel detector in a particle physics experiment was already in 1983 in a CERN experiment called NA11. Okay, so what is a hybrid pixel detector? Hybrid meaning, we love the word hybrid in detectors. So you see many hybrids. But in this moment, I mean with the hybrid meaning that we put the center at the front together with so-called bump bonds. These are little lead bonds, for example, lead or indium or whatever, a relatively high Z material, which is on the sensor and on the electronics, and then they're put together in a flip chip process, warmed up, and then the new spheres, new balls built, and with that we can connect then the two matrices. So you have one matrix for the sensor, and you have one matrix where the silicon, the readout is implemented. So that's a very nice solution. It was already the first pixel detector in particle physics was at the Delphi experiment, which was, I think, in 94. So really time ago. And so there are many beautiful things about it. For example, you can develop the sensor optimized for radiation hardness and go to one company which does spatial sensors, and you go for the electronics for a different company, and then you go to a third company and put them together, and then they are optimized, for example, for the harsh environment, for the high Lumi LHC or the LHC already. The downside is, of course, you have a lot of material. The sensors have to be thick enough to survive handling them. The electronics have to be thick enough. In general, this is so you have a lot of material. At the LHC, it was not such. There's also a problem, the big material. But at future, like the linear collider, FCC, or also the muon collider, one shouldn't go for these big detectors anymore. In the end, it was usually not the detector, the sensor, which was giving the material, but all the rest, the cooling and all that stuff. Anyway, you will find a lot of pixel detectors. So, 96. So that was the Delphi VFT, the very first pixel detector. There was the LHCb VLO. Then, for example, the phase 0 and phase 1 pixel detector from CMS were hybrid pixel detectors. Also, the very first Alice ITS was a hybrid pixel detector, very similar to the one from Atlas. Phoenix in the United States built a hybrid pixel detector. And this is, for example, an early upgrade in Atlas, which was also a hybrid pixel. So this is actually the state of the art currently for the existing detectors. So here, for example, another picture of how it looks like, that you have a sensor of a certain size, and then the chips are placed on them. So this is, of course, turned around now. And this is a picture of such a bump bond. So you heard maybe the word before, bump bond. This is this 50 micrometers thick, thin, small bumps which are between the front-end electronics and the sensors to make such a detector. So you have not so many wire bonds. You still need wire bonds, but you do not need to put the wire to each channel, which was actually a big problem also for the strip detectors. And here a picture how it looks like. Again, you can imagine how much work, handwork, is involved in there. And I think I see Beniamino is smiling. He was around when this was built, and and I think also stressed by it a lot. Okay, then also for the high Lumi LHC, we will be building pixel detectors. They are also about to be produced. For example, here's a nice picture of how it could look like. This is an earlier version. What is important is, first of all, the radiation tolerant is yet an order of magnitude to be higher. So that made a lot of work. We have to have in order to measure the pile up events better, we have to have smaller pixels. Therefore, the electronics had to be smaller, smarter. Then here, what I mentioned before, this eta coverage, we had it only to 2.7 in Atlas, for example, or 2.5 in CMS. But of course, people want to measure vector boson scattering and vector boson fusion. And with that, we should go with the tracking detectors to 4. And this is what is being done for the high Lumi LHC. And also because of the material, which has an impact on the momentum resolution, we had to build the detector. We have to build the detector much thinner. But I would like to go in my last, I don't know how much time, to next generation silicon detectors, because I showed you now hybrid pixel detectors. So the sensors with the bump bonds, with the front-end chip, this is what we have in all of our high Lumi LHC detectors, except for Alice, or the sensor here. But then let's dream a little bit. What do we want? We want to have the perfect pixels or strips for the next generation. Very small pitch, so meaning the width of a strip or a pixel size. So that we want to have in the order of 20, 25. We want to have the very thin material so that the active layer, the silicon itself, including electronics, is only 50 micron. Right now in the hybrid pixel detector, I'm speaking of 500. So that is actually quite a big difference. The readout speed should be very high. Of course, the timing, as we heard from Lawrence, should be very, very good. We want to have it super radiation hard. And very smart readout capabilities. But this is very, very difficult to have in the same silicon detector. All in one is impossible with the existing, with what I showed you before. And therefore, people have to work on the next generation pixel detectors in order to go somewhere. And the problem is also, while we are doing that, we always have to think about money. These detectors, the silicon detectors, are really not cheap. And therefore, we have to get smart ideas of how to do this huge square meters without the funding agencies getting too crazy about it. So going back to this dream of a good momentum resolution, I looked at all the various detectors which are being discussed. I don't have Maya. I should add this to my next version of this talk. I only realized too late that I could add this. So here's the muon detector and the tracking. I will not talk about the muon, which is also a tracking system, of course, but I will talk about the inner tracking. Mostly vertex will be in the separate ones. And when you look at what is upcoming Bell, ILD, SID, whatever, IDEA, Allegro for the FCC, EE, or also for the FCC HH people are discussing, you see in the end there is all over the place silicon strips. So this is definitely what we will go for, and large area. And what we have very often is, what we want to go for is that we actually go away from this, that we have a hybrid, but that we melt them together. That we have, we call that then monolithic, where we have then the front-end electronics on the same substrate as the active sensor. And that is called the monolithic active strip or pixel detector. And there are already quite a few around which are using that. For example, here the ITS from Alice, which was 1.5 years ago installed, I think. And it's a beautiful detector which is built out of CMOS. So the very first, no, it's not the first, but the very first large detector. So it has 10 square meters, so it's a relatively large detector built in this new technology. But what is this new technology? So this is, as I said, monolithic active pixel sensors. Very often we talk about maps because we usually mean it as pixels. That's then typically a commercial CMOS process, but not any process. This is something people really confuse very often. They think any CMOS process can be used for sensing elements, and this is not true. One has to be sure that we need to have some way to deplete a thin layer inside. And this is either that we have imaging processes. There are many imaging processes around because all the cameras in your mobile phones are done in an imaging process, or they are so-called high voltage processes, so some possibility to attach a high voltage on the backside of the CMOS, or some combination of both. So what we have is typically that we have, this is very thin, this is only 10 micron thin, this light area. We have a substrate, then there is this epitaxial layer, we call it, which is only a few 10 micron, 10 or 15, not more. And then there is the electronic on top, which can be already the readout electronics. And then we have then somewhere this N wells, which are used to make this PN junction. And then we get this PN, this depleted area in which we have drift, because there we have the electric field. But we also have diffusion because we can't necessarily deplete the whole maps. And this is something which is being studied by many, many groups. I called it myriads of studies ongoing, because if you look into the maps business right now, one gets dizzy very, very quickly, because there are so many processes which are being studied, so many different possibilities, how to optimize this, how to get this fully depleted, how to get the fill factor done, so meaning can we area, and so on. And one big problem is actually that this companies, we are working with the various companies which make the CMOS processes available, they don't tell us about the doping profile, like what is exactly the amount of borons in this N-type or P-type material. And therefore we have to do a lot of guessworking. And we have to be very careful and step on our toes, because if a process or if a company says he published something which was our company secret, you're not allowed to use it anymore. So it's really a bit of a difficult thing to get. For example, this is a process being used by Alice, the tower just process, but there are many associated with all the companies. And then we speak of non-disclosure agreements. You sign that you will get some information, but you sign you will not tell anybody. Try to make a publication with that. I mean, it's really a bit of a difficult business here. But nevertheless, it is the future, I think. For pixel detectors, this is the future. This is the way to go, I think. And therefore, we are following this up, because also other detectors will be using this technology. Okay, just very quick glimpse at it. We are also looking into the same for strip detectors, that we are also using this kind of processes to make actually strip detectors to go to large area. And this is just one project. There are not that many projects around which actually look at strips, because everybody is looking at pixels, because they are pixels, but one cannot necessarily always scale the pixels all the way to the larger area because of power consumption and so on. So one should, in my view, one should keep an eye on still on strip detectors, and therefore we are looking into CMOS as well. But then, for example, if you look at the vertex detector, and I hope this table is new, I hope I made it correct. I compared linear collider and high-lumi LHC and muon collider. And there you see that the material budget is at the linear collider, the most stringent one, but still the muon collider is also quite difficult. A single point resolution is comparable for the linear collider and the muon collider. Here mentioned also the timing by Lawrence, that's more difficult than, for example, for the linear collider, and therefore there are other technology which are also silicon-based being looked at in order to get to, for example, 30 picoseconds. But at the same time, is actually quite a difficulty at the muon collider. I think I skipped a little bit too much here now. So the vertex detector is the very innermost which we need in order to measure the impact parameter resolution. The single hit resolution is important for that, and the primary vertex resolution. And this is, for example, the resolution for this impact parameter, where all these parameters go in, for example, the multiple scattering and the single point resolution. And looking at that, you understand why we are looking, for example, that this material is very low here. So most goals were reached of this for the linear collider or the muon collider, but not in one pixel detector. And this is actually the challenge we have, for example, for the linear collider, to develop a pixel detector which can actually address all of this goal. And then in the next step, also for the muon collider, because then the radiation damage has to come on top there. Okay, so the solution is monolithic. And again, here the table of all the experiments which are under discussion. And if you look, oops, They are all maps. Maybe for the LHEC, there is a question mark added, and for the FCCHH, they also still put things on there with a question mark. But in general, you see here the maps, and therefore this is also then understandable by why there are so many different groups working on all these different approaches how to build a maps detector. That is actually my second to last slide. This is the dream of a tracking detector person going bent, because you can imagine the perfect detector layer would be a sphere. If we could build spheres and then read them out, that would be the absolutely dream. And but that's currently possible for tracking detectors. There is actually one calorimeter in the crystal ball experiment, but apart from that, for tracking detectors, it's currently not yet, but Alice is actually going towards building those to have them bend around the beam pipe, so that you already have not this layering and then have them overlaying, but that you actually have them bend around the beam pipe, and with that get a cool step towards the next generation detectors, and while at the same time really going to the extremely low material budget. And therefore, in my eyes, this is absolutely cool what they are doing there, and one should keep an eye on that. Okay, I think I will not repeat everything. Tracking detectors are cool. They are there to do the track and momentum measurement of charged particles. You've seen a quick overview about technologies, from how a silicon detector works to what are the different possibilities. And of course, challenges for the muon collider are huge to build a tracking detector there. But on the time scale, I think we can do it. And that's it. Thank you.
Okay, let's do a few questions and then we'll go to coffee breaks. Questions. I'm curious for the map. Nice to sort of this manufacturer detectors. What are maps for us? So why are they making maps, and what are they optimized for?
Typically, they build cameras for handies, mobile phones. I'm sorry, now we're speaking German. Mobile phones and other, wherever you need something imaging, larger cameras, not only for the mobile phones, and therefore, or it's relatively difficult to discuss with them, and it is very expensive to go for a run, we call it, or a submission. Right. That if we want to do a submission, we usually share the cost, go together with a few people, and in order to do that. And it will not only, I mean, we are right now still really discussing mostly the sensing element, which is the maps itself. But at some point, one also has to keep in mind that we have to scale it. And that is very often the really difficult thing. You can have a little prototype working beautifully, but as soon you have to cover 10 square meters, you really run into problems. And then one has to early on think about what other companies do we need, because we want to have, of course, a very light structure which holds the maps, because they cannot fly, and we have to see how still even so they might not need as much cooling. We still have to make sure that they don't run away in the temperature and so on. So a lot of other companies will come in at some point.
I see. Think there's any hope for other people who might have more money to sort of put pressure on them to be able to do the kind of manufacturing that we want to kind of, are there other applications that are more similar to?
I'm not aware of anything. It will always be an uphill struggle. And the one thing is, in general, with electronics and particle physics is, I mean, I didn't address it, but for example, the readout electronics for many things, they are the standard CMOS processes. We use 130 nanometer, for example, for the Atlas strips detector. We only have this technology still around because it is a process which is liked by companies who make things for weapon systems, because that's an electronics, which is a process. It's a process which is known to be radiation tolerant, and therefore that is the reason why it didn't fall off the desk. Other technologies just fell off the desk at some point, that the company says nobody wants this anymore. That's it. We will replace that foundry. And you are like, oh, we want to submit a chip next year. So that was also early in the LHC, high Lumi LHC discussions, a big topic. Shall we move to a different technology or not? But then it also takes a lot of time to go from 130 to 65, for example. And then 65 is also an old process, because for the chips in the computers, we are at 5 nanometers. So huge differences there.
So thank you. You mentioned time resolution as one of the goals or dreams for the next future applications. So I know for the CMS and that rates in avalanche die. Do the maps can get to that?
Not yet. We are not. We don't have that time resolution yet. But there are actually ideas of doing something similar, like LGAT structures into a maps, so that we actually combine the abilities of the LGATs with the maps, and with that getting faster maps, so that we combine the best of every world. But we are still early in the processes. We also try to understand a little bit better what is actually the reason for the signal being so slow inside the silicon, and with that we can actually maybe even work a little bit more on this field, so that we can actually get faster inside. But this is an early research which is still ongoing.
Any other questions, comments? Okay, then
want
we will
coffee?
do coffee break. Yes.
Thank you.
Thanks. Let's take our speaker again.